Jake Meyer doing my video for the Stack0 buffer overflow exploit from Protostar. So first off, if we look at the source code, we see that there's a character buffer here of 64 characters. This entire attack is largely based off of that buffer. We see it's 64 characters, so we know that if we entered 65 characters, then it would overflow. Our goal here is to change the modified variable. So what we're going to do is attack the stack in order to overwrite the buffer into the modified variable to change that value. So what we want to do is we want to use GDB and its tools in order to take a look at the stack memory behind the program in order to make sure that our buffer and our variable are located in memory where we think they are, and that they're going to behave as we expect them to as we try to execute a buffer overflow attack. So what I'm going to do is I'm going to set a breakpoint in main. I'm going to set my disassembly flavor to Intel, just since that's something that people are more familiar with. Then we'll do is run the program, and then we'll disassemble main here, and I'll talk a little bit about the code here. So here we have pushing our main function onto the stack, pretty typical across programs. Here we see that we're moving the value 0 into an address that is hex5c off of the stack pointer. And we can obviously tell that this must be the modified variable, since it's the only variable in the program that's assigned a value of 0. So now we know that at hex5c off the stack pointer is our modified variable. Now if we look here, we see that this address is moved into the EAX register, which is then used in the gets call. So this is the gets is what is used to get input for our buffer. So we know that this address that is used for the gets call must be the address of our buffer. So at hex 1c off of the stack pointer, we now have the address of our buffer. And if we look at actually the difference between hex 1c and hex 5c, we see that it is 64 in when converted to decimal. So we know that basically our buffer leads right up to the edge on the stack pointer where our modified variable begins. And then if we look down here, we see that we move this our modified variable back into the EAX variable. Then we test it for quality, and that gives us our if-else statement where we do a jump if equal, in order to check whether modified has been modified or not. So what we're going to want to do is use GDB's commands in order to change. In order to, I am making some mistakes, but so we obviously didn't modify the variable in this instance. But we want to do is delete all these breakpoints, and we want to set breakpoints where we can watch our buffer be filled up and see that overflow in action. So what we want to do is set a breakpoint right here where we call our gets, and then directly after it, so that we can see the effect that our overflow has on the memory. So we're going to set a breakpoint at 0x80480C. 80480C. And then we're going to set another one at breakpoint 0x048411. And what we need to do in order to see the registers and look at our stack and see that overflow in action is we need to define a hook stop, which is going to execute some commands every time we hit a breakpoint. So we want to see all of our registers We want to see the entirety of the stack. So we're going to use this command in order to do that, which prints out the stack pointer. And then we also want to see the next two instructions on the stack in order to ensure that we are in the correct spot where we want to execute these breakpoints. So now what we want to do is run the program. And we see in the stack here, it all kind of looks like gibberish, but if we look at the stack here, we'll see that there's only one instance of just all zeros. So this must be where our modified variable lies. So now we know where that is. Now we want to check, okay, what if I entered some input and tried to overflow the stack, right? Where does this end up? So we see that it starts right about here, and then it kind of goes down another row, and then we ended right about in this area. So since it's little endian, it starts from the little end. So we see that 4-1 is one character, so we have 4 of these per line. So we have, let's see, 4, 8, 16, 20, 24, let's try 28, 32, 36, 40, 44, 48, 52, 56, 60, 64, and then some extras, but we'll keep trying. So we haven't modified the stack variable, obviously. So if we know that the buffer is 64 characters long, let's just try that. So if we try to use 64 characters, where do we end up? So that's what I'm going to attempt to do. I'm going to run it again. We see that things are back to normal. Nothing's changed. I haven't entered anything in the buffer. Now I'm going to continue, and I'm going to enter, I'm just going to eyeball it, I think. But that seems about right. We haven't made it all the way, but we're on the right track. So the more that we enter, we get closer and closer to this zero variable, and eventually we'll be able to modify it. So if I just keep giving it a shot, we'll get there. And then I'll show you that there is a easier way in order to ensure that we're using the right number of characters. Okay, so now we've overflowed the buffer and we've reached into the modified variable and we've altered it. So now we see that it reads as all A's, and if we continue the program here, we'll see that we have changed the modified variable and we have succeeded in our goal. Now, if we quit out of GDB, we'll have an easier time overwriting these buffers by using, simple commands. So there's a Python command that is used in the video that is also very useful for all the other exploits that are on Protostar. So if the buffer is 64 characters, basically we want to print 65 A's, and that gets us just into that bottom range of the modified variable. And then we're just going to inject that as input into Stack0, and this should change the modified variable. So now we see that we have successfully overflowed the buffer, changed the modified variable using the buffer overflow attack. And this is why that gets command is so dangerous, is because it has no defense over any sort of buffer overflow, and really just allows you to go anywhere in memory that you so please. I think that's it. Thank you very much.